Okay, so hello everyone and welcome to the OneClass channel. My name is Donna and I'm a recent master's graduate from the Material Science program from the University of Ontario Institute of Technology, also known as Ontario Tech University. So today we're going to go over some commonly asked questions in chemistry at the high school, college, and university level. So if you needed any help with homework or tutoring, then check out the links in the description below. So now let's just get started on our set of questions for today's session. So the text is very big, but just asks, what is a half reaction? Why must the number of electrons lost in the oxidation half reaction equal the number of electrons gained in the reduction half reaction? Summarize briefly the steps in the half reaction method for balancing redox reactions. And also, what two items must be balanced in any redox reaction or in any reaction? So this is like a multi-step kind of question. But basically, a half reaction can be either an oxidation reaction or reduction. Okay, so they also show the transfer of electrons from one atom to another. So just to answer the second part of the question, why must the number of electrons lost in the oxidation must equal the number of electrons gained? So electrons lost is equal to electrons gained. And this is just because of the law of conservation of mass. So the conservation of mass just states that because matter cannot be destroyed or created, like if you had one electrons leaving, they need to go somewhere. So that's why you need the same number lost is equal to the same number gained. Okay, so the next part of the question just asks to summarize briefly the steps in the half reaction method for balancing redox reactions. And I'll pretty much just answer the next question, what two items must be balanced? Basically, your atoms must be balanced, and also you want to make sure the charges are balanced as well. So I'll just add those as part of the steps. So let's say we had an example. I'll write the example first. So let's say we had an example of an unbalanced reaction. Plus iodine or iodide makes xenon plus I2. So this is what a typical unbalanced redox reaction might look like. So the first part of solving a question like this is just to write reduction and oxidation half reactions. And also in this same step, we want to make sure that to balance the atoms as well. Okay, so the reduction reaction would be this xenon so you can see it goes from an oxidation number of like -6 because each oxygen has a -2 charge and there's 3 of them. Sorry, it goes from +6 to 0. So because its oxidation number was decreased, this is what got reduced. So I want to now balance the atoms. So you'll see that there are 3 oxygens on the reactant side and there are none on the product side. So in aqueous solutions, to add oxygen, I am going to add 3 H2O. Okay, so notice that now I have 6 hydrogens and 3 oxygens on my product side. So I'm going to balance out the hydrogens by adding 6 H plus to my reactant side. So now all the atoms should be balanced. And I can write down my oxidation reaction, which is the negatively charged iodine to I2. And all we need to balance here is we just need to put a coefficient of 2 to make everything balanced. Okay, so step 2 would be to balance the charges. So we do this by adding electrons. So if we look at our reduction reaction, you'll see that there are 6 positively charged protons on our reactant side, and on our product side, everything is neutral. So to neutralize these protons, then I need to add 6 electrons to my reactant side. And my product side just stays the same. For my oxidation reaction, I have 2 negatively charged ions. So to this side, I just need to add 2 electrons to balance out those charges. So what's also important with redox reactions, like we mentioned earlier, is that the number of electrons lost must equal the electrons gained for both our oxidation and reduction reactions. So for our reduction reaction, you'll see there are 6 electrons. So I need to have 6 electrons on my oxidation reaction as well. So I need to just multiply this whole thing by 3. And we end up getting 6 I minus plus 3 I2 plus 6 electrons. Okay, so now we have our electrons balanced. So step 3 is just to combine overall redox. So first, let's write all of our reactants down first. So this should be 6. And now let's write down all of our products. Okay, so basically when you get to this step, you want to cancel out anything that is the same on both sides. So in our case, it would just be our 6 electrons canceling out on both sides. And we are left with our net redox reaction. So let's double check that everything is balanced. We have 1 xenon on both sides, 3 oxygens on both sides, 6 hydrogens, and 6 iodine. And in terms of the charges, we have 6 positively charged protons, 6 negatively charged protons to neutralize each other on that side, and everything is neutral on the product side. So this is an example of the steps that you would take in balancing redox reactions. Okay, so let's see what the junior tutor said. So a half reaction is an oxidation reduction redox reaction which depicts the change in oxidation state of the atoms in the reaction. This change in oxidation state is brought about by the transfer of electrons from one atom to another. Oxidation reaction involves the loss of electrons, and its atom is called a reducing agent. Reduction reaction entails gain of electrons and functions as an oxidizing agent. An acronym can be used to easily remember main ideas in redox reactions. Okay, so I've never seen this one before, but they used LEORA, so lose electrons, oxidation, reduction agent, and GEORA, gain electrons, reduction, oxidizing agent. I personally use like LEOGR or oil rig, which is oxidation is losing and reduction is gaining electrons. But you can use any of these different acronyms. In balancing half reactions, it is imperative to balance the number of moles and electrons in a reaction to maintain the law of conservation of mass. A summary of steps for balancing reactions using redox is as follows. Step 1. Write the unbalanced ionic equations without the spectator ions. 2. Determine the half reactions, which atoms undergo oxidation and reduction. Step 3. Write the number of moles of the reaction that does not contain oxygen and or hydrogen, or balance the reactions containing oxygen by adding H2O. Then balance the number of hydrogen by adding H+. So this actually depends on whether or not your solution is in acidic or basic conditions. So when you're in acidic conditions, you would add H+. So this is your typical example, like a lot of examples are in acidic conditions, but just so that we are all aware, if we were in basic conditions, then we would just be adding OH- ions. But anyways, step 5, balance the charges for each side by adding electrons in the half reactions. Oh, here it is. So 6, for basic solutions, balance the reaction by adding OH minus in each side for every H plus ion. Then simplify by combining H plus and OH to form H2O. Yeah, so this is what you would do if you were in basic solution. Kind of adds like some extra steps. And they have an example of silver and zinc. Step 1, write the unbalanced ionic equation. So silver solid plus zinc 2 plus makes this silver oxide plus zinc solid. They identified the half reactions. So the zinc 2 plus got reduced because its oxidation number went from +2 to 0. And the silver got oxidized. It went from an oxidation number of 0 to +1. Step 3, no change for zinc, as there is a 1-to-1 mole ratio in the reactant and product side. Okay, so see the atoms are already balanced. Or, since there is one oxygen atom in the product side, add 1 mole of H2O in the reactant side. Then balance the number of hydrogen atoms by adding the corresponding number of H plus in the product side. Yep. And then step 5, balance the electrons lost/gained in the half reactions, then simplify. 6, add 1 mole of OH minus in the product and reactant side per 1 mole of H plus present in the equation to yield. So see here they added OH minus on both sides and H plus as well. Combine the OH and H plus to form H2O. So they pretty much just combined these two. And then simplify. Okay, so 2 zinc 2 plus, 2 OH minus. And everything is balanced in terms of the atoms. And also the charges. Yep, so this solution is correct. Okay, so on to question number 2. Is saying caffeine is the stimulant in coffee and tea. On has the molecular formula. So I'm going to write down the molecular formula of caffeine. It is C8H10 N4O2. Calculate the mass percentage of each element in the substance. Give the answers to 3 significant figures. So first, to answer this question, we will assume 1 mole of caffeine. So if we assume 1 mole of caffeine, we can find out how many moles of each atom there are in caffeine. Atoms there is. So for example, let's just do an example of how we would find the moles of carbon in 1 mole of caffeine. So if we look at our chemical equation, you'll see that there are 8 moles of carbon for every 1 mole of caffeine. So this gives us 8 moles of carbon. And if we multiply by the atomic mass of carbon, which is 12.01 grams per mole, So this value can just be found on your periodic table. Our moles will cancel out, and we're left with how many grams of carbon in 1 mole of caffeine. So 96.08 grams of carbon. So now if we were to do the same thing for hydrogen, I'm just going to skip and say that there are 10 moles of hydrogen. If we were to multiply it by hydrogen's atomic mass, which is 1.01 grams per mole, we end up getting 10.1 grams of hydrogen. Now for nitrogen, we have 4 moles of nitrogen. Multiply it by nitrogen's atomic mass, which is 14.01 grams per mole. And we end up getting 56.04 grams of nitrogen. And lastly, there are 2 moles of oxygen for every 1 mole of caffeine. Oxygen's atomic mass is 16 grams per mole. Multiplying these gives us 32 grams of oxygen. So if we were to add all of these masses up, we end up getting a total mass for caffeine. So total caffeine mass. So 96.08 plus 10.1 plus 56.04 plus 32 gives us 194.22 grams. Okay, so now that we have the total mass of caffeine, we can now find the mass percentage of each of the elements. So the mass percentage is equal to the mass of the component divided by the total mass multiplied by 100. Okay, so for example, let's start off with carbon. Mass percent of carbon is equal to 96.08 grams divided by the 194.22 grams, which is the total mass of caffeine. All of that multiplied by 100% gives us 49.47%. So that's how much carbon is in caffeine in terms of mass. For the mass percent of hydrogen, let's do the same thing. We have 10.1 grams of hydrogen divided by 194.22 grams times 100 gives us 5.20 mass percent of hydrogen. For nitrogen, we have 56.04 grams divided by the total mass times 100 gives us 28.85%. And lastly, the mass percent of oxygen is equal to 32 grams divided by 194.22 grams times 100 gives us 16.48%. Okay, so these are all of the mass percentages of each element. And if we were to add all of these values up, you know you did it correctly if it all nicely adds up to 100%. Okay, so let's see what the junior tutor said. The mass percentage of an element is the ratio of the mass of the element with the molar mass of the element expressed in percentage. Step 1 is to find the molar mass of caffeine. Okay, so they just pretty much, yep, so that's like the same thing as finding 1 mole of caffeine. They showed how the total mass would be around 194. And then step 2, find the mass percentage of each element. Yep, so they have 8 times the molar mass of carbon. So they pretty much just condensed all the steps. Yep, so this solution is correct. They got 49.48. The values are slightly different than mine because they used less significant figures for their atomic masses. So like instead of 14.01, they just rounded it to 14. But they pretty much got the same values, 28.86, 16.51. The solution is correct by assuming there is 1 mole of caffeine we can find the masses of carbon, hydrogen, nitrogen, oxygen, then calculate their mass percentages. Okay, so on to question 3. What is vapor pressure lowering? Okay, so vapor pressure lowering is a term that's used to describe the addition of a non-volatile solute. So by non-volatile, they mean a substance that is hard for it to turn into a gas, pretty much. So a non-volatile solute results in lowering the vapor pressure of the solvent. Okay, so we can also use Raoult's law to try and describe how the values of the vapor pressure may change upon the addition of a non-volatile solute. So for example, the pressure of substance A would be equal to the mole fraction of A times the pressure of A under standard conditions. Similarly, if we had the pressure of B This is equal to the molar fraction of B times the standard pressure of B, and the total pressure of this system would be PA plus PB. So you can see how, depending on how much of the other substance there is, this will affect the overall pressure, the new pressure of the solute and the solvent. Okay, so let's see what the junior tutor said. Vapor pressure lowering is one of the colliative properties of solutions. Example, boiling point elevation and freezing point depression. The vapor pressure lowering describe the phenomenon that the vapor pressure of a liquid will be lower when another compound is added to it. This means that the aqueous solution will have a lower vapor pressure than just the pure solvent. So this is the pressure of the pure solvent is denoted as the with the 0 at the top like that. And generally, the solute added is non-volatile, which is dissolved in the solution. So the vapor pressure lowering can be also described by Raoult's law of equilibrium vapor pressure, where PA is equal to the mole fraction of A times the pure solvent vapor pressure of A, and the pressure of B is equal to the mole fraction of B times the pure solvent vapor pressure of B. And then P total is just equal to PA plus PB. However, since the added solute is non-volatile, it does not contribute to the total vapor pressure of the solution. With this, the vapor pressure becomes only a fraction of the pure solvent vapor pressure, depending on the mole fraction of the pure solvent. So this solution is correct. Okay, so question 4 asks, how do you calculate buffer capacity? So question 4. So first, let's define what a buffer is. So these are solutions that resist changes in pH upon like small additions of either acid or base. So buffer capacity this is pretty much the measurement of the efficiency of a buffer solution. So this is like how well it resists the change in pH. So we can calculate buffer capacity by using the following equation. So we'll denote buffer capacity as this like beta, which is equal to N divided by delta pH. So here, N is the number of moles of an acid or base added per liter of solution. And delta pH is just pretty much the change in pH, which is equal to the pH of your final solution minus the pH of the initial solution. Okay, so pretty straightforward. This can also be written as B beta is equal to delta B over delta pH. So delta B is the mass equivalent of the added strong base or strong acid to change the pH level of 1 liter of buffer solution by 1. This is another way of finding buffer capacity. So depending on what you're given in a question, you can use either equation. Okay, so let's see what the junior tutor said. Buffers are solutions that resist changes in pH after the additions of small amounts of an acidic or basic solution. There's a factor called buffer capacity, which is the measurement of the efficiency of a buffer solution. The buffer capacity is calculated using the equations. Buffer capacity is equal to delta B over delta pH. Delta B is defined as the mass equivalent of the added strong base or acid on the buffer solution to change the pH level of 1 liter of buffer solution by a factor of 1. Buffer and the buffer concentrations are also related using the Van Sky equation. So they had beta is equal to 2.3 C times Ka times the concentration of hydronium ion, H3O+, all of that divided by Ka plus the concentration of H3O+ to the power of 2, where C is the total concentration of the constituent solution of the buffer. So this solution is correct. I'll also add the equation I had as well. Okay, so moving on to question number 5. When is the density of water 1 gram per milliliter? How can we measure density? So when the temperature is 4 degrees Celsius, water attains its density of 1 gram per milliliter. So we can calculate density by using the equation where density is equal to mass over volume. So depending on the mass of the sample, so it's the ratio of the mass of the sample to the volume of the water that is displaced. So for example, if you had like a brick or something and it weighs a certain amount of grams, let's say we had a brick weighing like 5 grams and like it displaced like 1 milliliter of water somehow, then its density would be 5 grams per milliliter. Okay, so let's see what the junior tutor said. The density of water at standard conditions, 1 atm pressure at room temp, is recorded to be 0.99777 grams per mil. So it's pretty much also just 1. But when the temperature goes lower, the molecules start to aggregate. When the temperature is equal to 4 degrees Celsius, water attains its density of 1 gram per mil. Why does ice have a lower density? This is because the water crystals have great space, hence not attaining the density of 1 gram per mil. Density of a material is computed using the equation density is equal to mass over volume. So going back to that ice question, since they have a much greater volume, when you divide mass divided by volume, ice tends to be less dense than water, liquid water. Okay, so they have density equals mass over volume. This is described as the ratio of the mass of the sample to the volume of the water displaced. If a stone with a mass of 10 grams displaced a water of volume 5 mils, its density is 10 divided by 5, which is 2 grams per mil. Yep, so this solution is correct. Okay, so on to question 6, which asks to draw the alkane formed when 4,5,5-trimethyl 1-hexyne is treated with 2 equivalents of HBr. So let's try to draw out this structure together. 4,5,5-trimethyl 1-hexyne. So it looks pretty complicated, but if we kind of just break down the steps, it's pretty easy to draw this type of molecule. First, we're interested in the parent chain. So in our case, it is a 6-carbon chain, and we know that because it has hexyne as kind of like the base. So let's draw a 6-membered carbon, 6-carbon long chain. And let's number them. So we have, start from here, 1, 2, 3, 4, 5, 6. So we can see that on carbon 1, that is where our triple bond is, since it is 1-hexyne. Let's draw a triple bond on carbon 1. And there are 3 methyl groups. So there's 1 on carbon 4. I'm going to draw it down here. So there's 1 methyl group on carbon 4, and there's 2 methyl groups on carbon 5. Okay, so now that we have all of our substituents in, we can just add the remaining hydrogens to our structure. And you also want to remember that carbon will form 4 bonds in total. So you can't have more or less. So let's say if carbon 3 was bonded to 2 other carbons, that means it can only bond to 2 other hydrogens. Okay, so in this question, 4,5,5-trimethyl-1-hexyne is treated with 2 equivalents of HBr. Okay, so what happens is an electrophilic addition reaction. Electrophilic addition. Okay, so since there are two equivalents of HBr, that means 2 bromine groups will be added to the triple bond. So in this electrophilic addition reaction, there's something called the Markovnikov's rule, which states that the bromine will be added to the carbon that has the less number of hydrogen atoms. So in this case, it is carbon number 2. So knowing this, we can draw out our product. So pretty much everything else stays the same. Let's just draw everything else the same. And on carbon 2 is where the 2 bromines will be added. And we no longer have a triple bond. It is now just a single bonded carbon, CH3. So if we were to name this compound, let's number it again. But this time, so we have less numbers involved. Actually, let's see. If this was... Yeah, I think there would be less numbers if we numbered it from the left. We have 2 bromines on carbon 5. So it would be 5,5-dibromo. And then on carbon 2 and carbon 3, there are methyl groups. So 2,2,3 trimethyl hexane. So let's test to see if we numbered this as carbon 1, just to see how it compares. We would have 2,2-dibromo, and then 4,5,5-trimethylhexane. So this number is 4, 5, 6, 7, 17. And for the name in blue, we have 14, 15, 16, 17, 18. Okay, so this is why the name written in black would be correct, since it has the less numbers in the name. Okay, so let's see what the junior tutor said. The structure of reagent 455 trimethyl 1-hexyne is given below. Treating this with two equivalents of HBr will undergo electrophilic addition reaction. For the first HBr treatment, bromine will add to the carbon attached to the less number of hydrogen atoms according to Markovnikov's rule. The reaction yields 2-bromo-455 trimethyl-hex-1-ene. So this is only if one HBr was added. They show what it would look like. And then using Markovnikov's rule again, the alkene formed in the first step will react with the HBr in the second treatment via addition reaction. Hence, the alkane that will be produced is 5,5-dibromo 2,2,3-trimethylhexane. Yep. So this solution is correct. Okay, so question 7. The heat of vaporization of water is 2,260 joules per gram. How do you calculate the molar heat of vaporization of water? So this question looks like it would be hard, but it's actually not too difficult. Molar heat of vaporization of H2O. So they give us the heat of vaporization. So the difference between molar heat of vaporization and heat is that the molar heat of vaporization depends on how many moles there are of the substance. So if there was only 1 mole of water, it would have the same value throughout. So the heat of vaporization, 2,260 joules per gram. To calculate the molar heat of vaporization, so this is for 1 mole of water. We need to just multiply by the molar mass of water, and we do that to cancel out the grams and to get our answer in joules per mole. That's why molar heat of vaporization is interesting to use, because this is dependent on how many moles of water there are in the system. So this value will be the same throughout, like any of the tables that you might get in your test or in a textbook. And it is 40,680 joules per mole. And we can calculate this to kilojoules per mole. Just by dividing by 1,000, you get 40.68 kilojoules per mole. Okay, so the junior tutor said, using dimensional analysis, calculate the heat of vaporization in joules per mole. Use 18 grams per mole as the molar mass of water. Multiply the given heat of vaporization by the molar mass of water to cancel out the gram unit, and they got 40,680. Okay, so this solution is correct. Okay, so question 8. Classify each solid as a covalent, ionic, metallic, or molecular solid. And they have diamond, frozen carbon dioxide, pure sodium, and sodium sulfide. Okay, so first let's write the definition. All of them. Covalent This is between two nonmetals sharing electrons. So out of all the options that they gave in the question, a covalent solid would be diamond, since it's basically just carbon and hydrogen. So for ionic, this is between a metal and a nonmetal. So for example, out of the options given, this would be sodium sulfide. So sodium would be our metal, and sulfur is a nonmetal, and they come together to form an ionic bond. Metallic. So metallic solids are when you have metal cations, so positively charged metal ions held together by delocalized valence electrons. So an example of a metallic solid would just be pure sodium. So it's not bonded with anything else, it's just pretty much sodium ions that are held together. And lastly, molecular solid. So this is when you have molecules held together by intermolecular forces. So molecules are also nonmetals. And lastly, this example would just be the frozen carbon dioxide. Okay, so the junior tutor said that covalent bonds involve the sharing of electrons between atoms. Metallic bonds have a strong electrostatic force of attraction between the cation and the delocalized electrons in the geometrical arrangements of the two metals. Ionic bond is formed between a metal and a nonmetal. Diamond possesses a non-molecular covalent network. CO2 is a covalent molecular solid. Sodium exhibits metallic bonding. And sodium sulfide is also non-molecular ionic solid composed of Na+ and S2- ions. Yep, so this solution is correct. And I think we have time for one more question. Question 9. How can you determine the empirical formula of magnesium oxide? So generally, to make magnesium oxide, we have magnesium plus oxygen makes magnesium oxide. So since we don't know the empirical formula, I'm just going to put MgXOY. So typically you might be given the mass of magnesium and the mass of oxygen when you would have a question like this. So let's say we had a mass of magnesium equal to 0.124 grams. And we had a mass of oxygen. I'll just put mass of oxygen, like a single oxygen atom, is 0.071 grams. First, we would find the number of moles of both of them. So we do that by dividing by their molar masses. So the molar mass of magnesium is 24.3 grams per mole. So this gives us a number of moles of around 5.1 times 10 to the negative 3 for magnesium. And for oxygen, it is 0.071 grams divided by its molar mass, which is 16 grams per mole. So its number of moles is 4.4 times 10 to the negative 3. So this was step 1, finding the number of moles. Step 2 would be to divide by the lowest number of moles. So let's write out our empirical formula. So the lowest number would be the 4.4 times 10 to the negative 3. So I'm just going to show how you would divide it. And a number divided by itself is just 1. So 5.1 divided by 4.4 is around like 1.1, but we're just going to round it to 1. And oxygen is just 1. So our empirical formula is just MgO. And the junior tutor said, to determine the empirical formula of magnesium oxide, the following steps and calculations must be done. Calculate the number of moles of magnesium and oxygen based on the mass. The mass can be determined from the percent composition of magnesium oxygen in a compound. Okay, so they might give you percent composition, but basically you just need to find the masses. After you find the mass, you can calculate the mole ratio by dividing the number of moles by the smallest value among them. Write the empirical formula with the mole ratio as the number of atoms. So this solution is correct. And I also mentioned to just round. Sometimes you might get something like 2.9. You just need to round it to 3. Okay, so that is all for the questions. And if you enjoyed today's Q&A and you'd like to be notified of when we do this next, please hit the subscribe button and notification bell below. And if you'd like to submit a question of your own, then check out the links in the description. And don't forget to leave a like and a comment if you enjoyed today's video. And you can share it with your friends and classmates if they needed any help with chemistry. This has been Donna from OneClass, and I hope to see you soon.